Yeah, what time is it right now?
It is 6 minutes after. Okay, I think we're going. I think we're.
When do you want me to go?
Yay.
Hi. All right.
I don't know what happened before.
Yeah, I don't know. I kept clicking on it, and your face would show up, but it would be totally frozen, and then it would look like something's loading, and then it would tell me to go to hell. So I don't know. But here we are.
Yeah.
Hi, Mel.
Yeah.
Okay, so I'm good. How are you?
I'm okay. Yeah, I'm okay.
Yeah?
Yeah. It's cold outside, but it's sunny, so that's the good thing.
Yeah, I went for a little walk before this, and I don't know if it was snowed or drizzled or what, but it was fresh, and I didn't mind it.
Yeah, I saw some flurries indoors, but yeah, I saw it like flurrying earlier. Yeah, this is the longest I haven't shaved. I think maybe comps. I probably didn't shave around comps, but yeah.
Okay.
Yeah, it's
look good.
not going anywhere, so.
I like the mustache. I think that looks good.
Yeah, thank you. So you are sharing some cool physics at home.
Yeah, so I think I maybe alluded to this last episode. By alluded, I think I might have just said it, but I've been helping design some first-year lab courses, or labs, for a first-year physics course to be taken this summer. So usually they go into the lab and they do all this like buy a recipe book kind of thing labs, very first year-ish. But now obviously they can't go into the labs. So we thought we would try to design 4 labs and mail them a bunch of stuff and have them do it at home. So
that's so innovative.
Yeah, and I think it's going to turn out really well. So the materials have arrived. So I have one of the lab kits, and I've been writing the manual, and now I finally get to try it with the stuff that they'll have at home. So maybe I was hoping to show you some of this stuff.
I can't see anything. Am I supposed to be seeing equipment things or no?
I'm going to show you equipments now.
Okay.
Yeah. And I have a special guest today that might help me out. My girlfriend Andrea is over here.
Yay!
Call her over when needed. Otherwise, otherwise she'll just laugh at me, and it'll be good. So students will receive this in the mail. There's a box, and inside the box there'll be some materials. So this is what they get.
A protractor, a compass.
Yeah. So
a ruler.
Just in case. A protractor.
Yeah.
A rubber ball.
Rubber ball.
And a little spring. This is they called it a fishing lanyard. I don't know. I think you can put your keys on it, but
yeah.
Springs.
Ooh.
Oh, I guess this as well. It's just a plastic dish.
That's part of the experiments?
Yep.
Wow, okay.
And so with these materials and like pencil, paper, maybe some cardboard, you're going to be able to do 4 different labs. Some of them on forces and free body diagrams, some of them on conservation of energy, optics, and projectile motion. So minimal equipment and maximal fun and learning, in theory.
How does that work? Is it that you, like, are they going to have like video cams on them while they're doing the lab? Like, it's a big WebEx thing where they all go online, or do they take a video of what they do? Like, what's the format going to be like?
Yeah, so the format is going to be, let's see, maybe you'll be able to see it on my screen here, but they'll have a lab manual with prompts, like so.
Yeah.
And then directions on how to do their experiment and spots in the manual for them to fill in data. They'll just submit, they'll submit their spreadsheets or any plots that they make, just as a document.
Right.
We'll also ask them to take a picture of their experiment or something from their time doing this stuff, just like a photo, just for fun, just to see how people, improvise or,
Yeah.
I don't know.
So do they do it all at the same time, or can they do it whenever they can throughout the week?
Whenever they want throughout the week.
Mm.
Yeah, so it's pretty free form. It's sort of a do your best with the materials you have, but here are some of the materials, we'll send it to you. And hopefully they're going to learn a lot. It's going to be very hands-on, obviously.
Yeah, yeah.
I think it's going to end up better than the labs as they are with all the really fancy equipment and stuff. I think they're going to learn more here.
Yeah, because like they're doing it with things at home, first of all, and secondly, they're literally doing it on their own. They don't have their TA over them hovering like, oh, connect this to this, or like they're going to have to problem solve on their own. And yeah, that's
one of my favorite things is that the data acquisition, it's very much do your best with what you have.
Yeah.
Alternative, when they're actually in a lab, a lot of the time they have like computer situations where it just takes massive amounts of data. They might not know really how the data is getting collected. It's kind of removed from what's actually happening. So for example, the first lab is sort of a figure out how to do your graphing and figure out what programs you're going to use. When very basic experiment, it's just going to be basically taking your rubber ball and dropping it. Uh-oh. We have a ball predator. Come here.
Oh, Cayenne?
Yeah. So the first lab, all we're really doing is we're measuring out 2 meters above the ground, setting up a camera, like a phone camera, hitting play, and then dropping it, and then using the timestamps on the video to measure out displacement over time.
Oh, wow.
And so you have the basic kinematic equations of like gravity has an acceleration of 9.8, your initial velocity is 0, you have your timestamps. And so what we want them to do is plot displacement over time, turn that into a velocity over time, turn that into acceleration over time.
Wow, I miss physics. This is making me miss physics.
Yeah, and then you don't have to plot anything or take data for the other parts, but it'll be like throw the ball up in the air and draw free body diagrams.
Right.
In that case, you're learning that when the ball is traveling, there's only one force acting on it, that's gravity. And then you can do some fun calculations, but that's sort of a warm-up to get them ready for the other labs.
Yeah, like what do you need the protractor for?
Yeah, so that's going to be the optics one, and that's going to be the kind of the hardest one to show. So maybe I'll show you the other ones first, and then I'll get to the protractor. But the second lab is on forces, and so typically when you talk about hell yeah, and friction. Do you remember friction?
What's the symbol for that? Is there a symbol?
The friction coefficient is usually done as mu. There's a kinetic and a static friction.
I don't remember. Oh, it sounds a little familiar.
Yeah, so it's proportional to its mass times gravity, basically the normal force. So if you have a object resting on the ground, gravity is going to be accelerating it down into the ground.
Yes.
With some mass, and then because it doesn't, slip through the floor, that means the ground has to be applying a force upwards.
Yes.
So here's an object of known mass. It's sitting on our box. We're going to pretend the box is massless. So this is about 500 milliliters, and it's roughly water. So we can say that that's half a kilogram. So now we know exactly how much gravitational force is acting on this. And so when we're talking about force... What's that?
How do we know how much gravitational force is acting on it?
So acceleration of any object on Earth due to gravity is 9.8 meters per second squared.
Okay.
And then the force of gravity is just proportional to the mass of the thing that we're interested in and the gravitational acceleration. So that's the F equals ma.
Right.
So then we get
Right. Okay.
half a kilogram times 9.8, and that gives you something in newtons.
Right.
So we have something of known mass. We have the gravitational force on it. So from that, we can calculate the normal force.
I did this experiment. Yes.
Yeah.
And like you pull it along and like you can measure you measure something. You can't remember what is that how you get the friction?
Yeah, so if I start pulling on the object here,
Yeah.
I can apply a force and it doesn't move, doesn't move, doesn't move until suddenly it starts to move.
Yeah.
So at that point, so before it starts to move, what are the forces acting on it? There's friction keeping it still, and then there's this spring force that's trying to move it that way. So right at the point where it slips, the friction force, static friction force, is equal to the pulling force.
Yes.
But the problem here is we don't actually know what our pulling force is, right?
Right.
So we have this spring that we've attached to our object and we're pulling it, but what is that actually, what is the force we're pulling with? Well, we're going to get them to calibrate this spring and turn it into a force sensor. So the way we're going to do that
at home.
So everything you need is actually right here. So one of the nice things about springs that we teach them in 1A is that spring force is proportional to how much the spring is stretched. So if you stretch it by a certain amount, that's going to take a certain amount of force. And if you double that, it's going to be double the force.
Okay.
So again, this is only proportionalities. So we don't actually know the true value of the force that we're applying on the spring. Well, to figure that out, we would need to know the spring constant of the spring. So basically how stiff the spring is. Turns out we can do that if we have an object of known mass. So again, we're going to go back to this can. This is half a kilogram. What we can do is we can measure the natural length of this spring from here to here. Then if we attach our spring to this can and we suspend it, we basically just let it hang, then we can measure the length again and compare those two lengths.
Ah, so that's how you get the proportionality.
Exactly, yeah.
Ah.
So if it stretches by, say, like 10 centimeters, then we know that the force of gravity on this, which is 1/2 times 9.8, is equal to the force required to stretch this 10 centimeters.
Right.
And so now from that we can get the spring constant, which lets us relate any stretching to an actual force with a number.
Yeah.
So they only have to do that one time.
Yeah.
Then this spring has become a high-tech force measuring instrument.
Wow.
So once you have that, we can go back to this situation where we start with a spring, it has a length, and you slowly pull it, pull it, pull it, pull it, pull it, and right when it starts to move,
You measure that?
yeah, exactly, mark how much it's stretched. And then subtract that number from its original length,
Yeah.
multiply it by that spring constant, and you have an exact force.
Wow. Wow.
And so, yeah. Then the challenge part of, so the way we have it set up is we start with a problem that sort of gets them thinking in the right space. So it's just written on paper, like a little quiz problem that's directly related to the experiment. We get them to do an experiment and take data. And then we have a challenge part of the experiment where we try to get them to take some data, but it's going to be a little bit difficult, so it's just sort of bonus. And so the extra bit for this lab, finding the static coefficient of friction, not so bad. We just described how to do that. But there's also kinetic friction. So once it starts to move, there's a different value of mu. There's a different type of friction.
Yeah.
So this is a little bit more difficult to measure because if you're exactly the same velocity at a constant velocity, then we know that the acceleration is 0, and so there's no net force.
Right.
So that means that whatever length the spring is at, that's going to be related to the kinetic friction. But the problem is that if you don't pull it at a constant velocity, if it speeds up and slows down, then you're going to get different lengths on your spring.
Right.
Just sort of zigzag back and forth.
Yeah.
So you just have to be very careful and consistent with pulling it. And just a little bit.
How would you know if they, like, how would you know if it's right? How would you know if their answer is right? Because, as you said, they could be pulling it at different velocities, potentially, compared to a constant.
Yeah, so we're going to suggest that they do the measurement 2 or 3 times. So if they're accidentally making it speed up, like it starts constant and then goes faster, the spring will be a little bit longer than it should be.
Right.
Maybe it'll measure a higher force. But if you measure it a little bit short, like if it stops and starts and stops and starts, you might get something that's a little bit lower. So if you do it a couple times, you will hopefully get an average value that's pretty close.
How would they even go about measuring that? Like, how do you estimate that? Do you just like open your finger like this and put it over the ruler? Because it's moving and you're trying to get the ruler to measure it at the same time. Like, how do you do that?
Yeah, so we're going to recommend setting up a little experimental platform like this.
Okay, so you came prepared.
Yeah, so if you start off here, you get it to slide along the paper, and then maybe put your finger down, and like you said, just try to like ballpark it. And you're not going to get an exact, perfectly done measurement. If you do it a couple times, you'll get sort of a range, and then you'll % of the actual value with this method. So it's better than nothing. Also,
question. So
yeah.
Are they also going to compare class data? Because if they do it on different materials, I guess, like under the plastic thing, it will have a different friction, right?
Absolutely, yeah. So that's going to be actually pretty fun for the TA. Well, fun for the TAs is maybe a stretch, but it'll be interesting for the TAs for sure. And that's something that the profs will talk about in their lectures. After the fact, when people submit their results and everything, that just provides more talking points for the TA or for the teachers. So that's
a great learning moment.
Yeah.
For you, at least. I'm not TAing this summer, so I don't have that. But yeah, wow.
So the third lab is maybe one of the harder ones to explain because there's some calculations that go into it. But I prepared a few of the calculations. I don't know if this is the right. No, it's backwards, isn't it?
Yeah.
Okay. Well, I'll explain as we go, and hopefully this will just be fine. So we talked about forces in the second lab. In the third lab, we want to talk about conservation of energy. So basically the idea is that energy is conserved in a system unless it loses it somehow, which is kind of a silly thing to say. But if energy is fully conserved in this ball drop experiment, I dropped a ball, it hits the ground, then how high should the ball rebound?
Doesn't that matter on... You're not pushing it down, you're just letting it drop, right?
Right. If I let it drop, it hits the ground, and all the energy is conserved, how high should it come back?
If all the energy is conserved, it should go right back to the original state.
Yep, that's right. But if you do the experiment, you find that that's never really the case. So that means
it's transferred to the thing that it's hitting, right?
Yeah. So a perfectly elastic collision, all the energy is conserved, and the ball comes right back to my hand. A perfectly inelastic collision, all of the energy is lost from the ball into whatever material, and the ball just sort of sticks to the ground. These are like two extremes, and in reality, basically nothing is perfectly elastic or inelastic.
Yeah.
So that's what we want to explore in this lab, and we're going to do that with the bouncing ball situation. So on paper, it's a lot easier to like calculate how much energy is lost. Something like this, you can, just in your brain think, okay, how high did it bounce this first time? How high did it bounce the second time? And then use like gravitational potential energy to figure out how much energy is lost. That's the idea, that it takes a certain amount of energy to raise the ball from the ground up to here. Mm-hmm. And then if you let it go, it releases that energy into kinetic, and then it goes back into gravitational potential.
Yeah.
So in theory, you could drop it, measure how high it goes, and then take that as the new energy state, drop it, it comes up to a different spot, take that as a new energy state. But if I were to do that for you right now, it would be hard to measure exactly the height that it bounces.
Yeah.
But we learned in the first lab about acceleration due to gravity and forces. So we know that when a ball is just in the air doing free fall, or throwing it up or something like that, the only force we have to worry about is gravity.
Right.
We know that right at the ground, when it first hits the ground, or when we first drop it, the velocity is at 0.
Mm-hmm.
So then we can use some simple kinematic equations to calculate, velocities, sort of change in velocities of the ball as it's going throughout its path, and more or less figure out the time between bounces.
Okay, so time could be a proxy for how much energy is being spent.
Yeah, so if we can't measure the height that it bounces between bounces, instead we can measure the time.
Mm-hmm.
And since we know velocities at 2 different points, and we know acceleration due to gravity, that's all we need in the kinematic equations to figure out the height.
Mm. Yeah, I don't know anything about the kinematic equation, so.
Let's see here. So that's like the, I think usually you see it as like change in distance is equal to initial location plus velocity times time.
Okay.
So if you're traveling at like 10 meters per second for, so if you're traveling at 10 meters per second for 1 second, you've traveled 10 meters.
Okay.
But then you also have acceleration in there, and that is related to displacement by time squared.
Yeah.
Yeah. So that's the basic kinematic equation. And so if we know like initial height and bottom height, like when it's hitting the ground, we know that delta D. If we know initial velocity, which is 0, and if we know A, or acceleration, then we can turn that big equation into something that lets you predict time, or sorry, bounce height as a function of time. So then the measurement that they make is they start at a certain height, drop the ball, and right when they drop the ball, they hit record on their phone for an audio recording. And then each bounce is going to have a sound. And then they can just look on the wave file and point out where each peak of sound is. Wow. Yeah.
Yeah, cool.
Then turn that directly into amount of energy lost or energy saved, however you want to calculate it.
Where does the energy go? Like, where is it?
So
when it's up, it's potential. Then when it's moving, it's kinetic.
Mm-hmm.
Then at the point it hits the ground, is any transferred to the ground?
Yeah, so you definitely lose some in terms of sound.
Yeah.
That's like one of the classic ones that students will say, but not a lot is lost through sound. You'll lose some into the ground. You can imagine, like, if I were to drop this ball onto like a sponge or something, the sponge deforms, and that's going to eat up some energy. But even like the wooden floor is going to deform a little bit, not a lot, but to some degree. What really ends up deforming quite a bit is the ball, the rubber ball.
True.
So that's going to impact, deform, and then all that squishing of the rubber material is going to suck some energy out. It'll, in theory, heat up a little bit. That also causes some energy to be lost. But yeah, that's enough for it to basically not come back to your hand and start bleeding from the system.
Wow.
So you could do that on the floor.
Yeah.
But then we're going to ask them to do it on different materials too.
Like their bed, it's not going to bounce.
Yeah. Or like their cardboard.
Yeah.
Or a piece of paper. You can put like a piece of paper on top of the floor, and that'll even be a bit different.
Yeah.
And then from that, yeah, it might be a little bit hard to hear that on the sponge, but I mean, we're not going to tell them what to use necessarily. It'll be up to them to try out different materials. So that's a fun one that it's more calculation driven, so it's a little bit more complicated to talk about, but I think it's one of the cooler ones.
Yeah.
It probably will surprise people that you can learn so much about a system with one simple measurement. Okay, so then we get to the last one. The one with this dish. What's that?
With the protractor.
Yeah. So this is going to be an optics one. Are you familiar with Snell's law?
No.
You know who? So this is like the whole, if you have a glass of water and you stick your pencil or a straw in it, you'll see the straw go down, and then you'll see like a zig.
Okay, yeah. Is it about diffraction?
Yeah, refraction, reflection, diffraction, all that stuff, all that good stuff. So that's what we want to teach them about in Lab 4. So one of the things that defines how much the light gets distorted is the material's refractive index.
Yes.
So this is just a ratio between the speed of light in a vacuum compared to the speed of light in that material. So we know vacuum is just a constant value. It's really big. But when light goes through any other medium, the light will slow down.
Is it 2.998 by 10 to the 6 or 8 or something like that?
Yeah, I always get it confused because it's either quoted in meters per second or kilometers per second, and that tells you whether it's to the 6 or to the 8 or whatever.
Wow, my memory. Amazing.
Yeah, so we can't measure speed of light, unfortunately, in this lab. Although, actually, we can kind of measure it. But what we want this is not going to work exactly the way I want, but we'll start here for now. What we want to do is we want to figure out what the refractive index is of our liquid. And so what we're going to do is measure how much the light is distorted and relate that back. So this is brutal. What we're going to do... Yeah, maybe. All right, here comes Andrea, our assistant.
Hi, Andrea.
Hi.
So if you can actually put it low so that it's sort of in plane.
I can't really see.
This is brutal. You can kind of see.
Yeah. I can.
Okay. I can get this even flatter. Let me try to just pull this off here. Oh, I turned it around. Okay. You can just leave it like this now. So you can probably see my finger.
Yes.
It's pretty much straight. I'm going to fill this with liquid now.
Ooh, carbonated.
It still appears pretty straight.
Can you see it like above and below?
Well, now it's gone. I don't know
I
what you're
can't
trying
see
to-
it below. I think it's because it's, I don't know if it's because of the bubbles, though. There's slight distortion, but it looks pretty straight. Oh, okay, yeah, I see now at that angle.
So that's actually the phenomenon that you're going to try to use. So if you look straight on, then you shouldn't really see any distortion.
Yeah.
Yeah, at a certain angle, you're not going to see any distortion. But as you change the angle, that's when you start to see.
Yeah.
So what we're going to get them to do is basically look through their prism and mark where they're observing, like where the line of sight is through the back end, and then mark where they see the object on the other side. So now we're gonna, and then draw a box
And
around
then
their.
Right, and then you use a protractor to then use the angles to estimate the refractive index or something.
Yeah, so you can draw a ray from where you're observing into the prism,
Yeah.
and then you can draw from that prism to where you see the object again on the other side.
Mm-hmm.
And so you're gonna get a line, an angle, and then a line with another angle associated with it.
Right.
So you're gonna get two different angles out of that. You're gonna get the angle of like my eyesight into the box, and then the angle of the object on the other side to the box.
Right. Then like you just put the marks on the paper for those like spots.
So I'm gonna quickly draw a thing on the paper.
Picasso.
I don't know. And so as I was looking through, it came in here.
Yeah.
And then if it went straight, it would have went out here. But where I actually seemed to see it was like,
I can't see. Okay.
here. So you can draw.
I can't see where you're drawing.
Okay. This is maybe not working exactly.
I saw some, but okay, yeah, this is better.
Okay. So this is where my eye was coming in.
Yeah.
And I should have seen the finger over here, but really I saw it over here.
Yeah.
So we know that no matter what material light's going to go straight. So it comes in here, it leaves here, and then you join the line here.
Mm-hmm.
So you're going to get an angle here, and you're going to get an angle here.
Yeah.
And if you relate those two angles, it'll tell you the index of refraction, or basically how much the light is slowed through the fluid.
Mm. Yeah. I remembered I didn't actually do this experiment, but I remembered learning about this when I don't know, I was 15 in physics.
Yeah, so then they can do that with water, and they can do it with oil, and they'll get something different.
Yeah.
And then, so that's like the basic experiment. And then the challenge experiment is more of a theoretical thing, but it's something that they can do. So the thought experiment that you want to kind of think about is if you're, say, under the surface of like a lake or something, and you're looking upwards towards like the sun or like a dock or something, you're going to have the speed of light going to your eye is going to be slower than it is outside of the water.
Mm-hmm.
So it's going to be the same sort of like bent light path, but it's going to be bent in the opposite direction than what we saw before.
Right.
So light is slower closest to you and faster away from you.
Right.
And this
Actually,
sets
I
up
talked about this yesterday. There was a tweet. I saw something on Twitter, and it was about the Doppler. Is that it? Something effect. Redshift. Something about redshift.
oh, that's like a if a siren is coming towards you or away from you, and the pitch
Yeah.
changes.
But it's also about colors too, because red is on the lower end of frequencies, whereas blue is on like the higher end of frequencies, and they use that to estimate where stars are, like if stars are moving away or towards us, and that's stars going away because they're more of on the red spectrum, something like that.
Yeah, that's actually a super important physics thing for astronomers in trying to figure out the size of the universe.
Yeah.
So, like you said, if it's moving away from you, it stretches out the wavelength. So it goes from, whatever wavelength it has to something that's more red into like the infrared, into radio waves or whatever. If it's coming towards you, it actually compresses the wavelength. So then you get into the blues and the like, X-rays or whatever.
So is that kind of
so I can tell you. Sorry?
explaining? Is that kind of similar to what you're explaining?
It's similar in that we're modulating the speed of light, but we're not exactly using this to measure speeds so much of like moving things. But this is similar to how gravity can lens light sometimes, and you can use that to like measure black holes. A little bit similar to that.
Yeah. Cool.
But the cool thing about being submerged and looking out is that depending on what angle you're looking out at, it's possible that the light doesn't actually escape the surface of the water. So if you look directly up at the sun or something, there's not going to be angle shift. That's like when the finger was just like straight in front of you and nothing changed. And as you rotate it around it, you've got more of a angle or whatever, angle change. If it's changing in the opposite direction, like you're going from slow to fast, you can actually shift enough that the light hits the surface and bends enough that it goes parallel or back down again.
Yeah.
And so that's called a total internal reflection.
Yes, I learned that too in diamonds. Diamonds.
Yeah, that happens a lot there.
Yeah.
But also like optical fibers for sending data.
Yeah.
It's the principle that your like optical cable operates on.
Yeah.
That's how it sends. Yeah. So we want them to try to calculate as a function of refractive index what angle you have to be looking out of the water basically to have everything be reflected.
Mm-hmm.
So yeah, I guess you can think about if you're like laying at the bottom of a pool, which is a bad idea, but if you're doing that and you look straight up at an object, say there's like I don't know, somebody's holding like a flag or something directly above you, if they rotate around you at a certain angle, you're not going to be able to see the flag anymore.
Yeah. Science.
Yeah.
Cool.
So yeah, that's
sure your students are hopefully they're curious, but they're going to have lots of fun if they're curious.
Yeah. And like worst case, I think you can get through these pretty quick. So
Yeah. And it's only 4 weeks, right? You said?
4 different labs. I think the whole semester is 7 weeks.
Oh, wow. That's long. I guess that is what it's normally, though.
Yeah,
I think. I don't know.
I think so.
Yeah.
That includes like their final exam and everything. So
Yeah. Cool.
it gives them time to work through stuff and
Yeah. Fun. You should let us know how your students enjoy it or what they found.
yeah, it's we've been planning this since near the end of March, and I think yesterday we finally got it approved by the university to mail these kits out.
Yeah, because I guess
we had to.
I guess they had to assess.
Yeah, we had to convince the crisis management team, and
Yeah.
it was
But it's probably
lot of
cheaper for the university to do this instead of using expensive equipment in the labs.
Oh yeah, if they had been doing this from day one, I mean, last year we just bought, I think, 40 really fancy computer chairs for the lab
Yeah.
because the chairs were old, and 40 times, I don't know if they got a special deal on them or something. If it's like $100, then we're talking like.
Yeah, that's still a lot of money.
And there, I mean, there's full-time lab technicians. I'm not going to say that we don't need them. Like, we need them to do these like labs and to manage these labs. But if all of these were designed to do at home, then I don't know, you're saving money on people.
Yeah.
It's going to be less work for the TAs, that's for sure.
Yeah.
So TAs are going to like that.
Yeah. Well, interesting times. You have to adapt, I guess.
Yeah.
Yeah. Cool. Oh wow.
Yeah, I'm kind of looking at.
Oh.
What time is it?
12:48.
Weird.
It doesn't matter.
Well,
nothing matters anymore. It's the end of the world.
Nothing
That's
matters. I agree, Andrea. Yeah.
She's doing homework, I think. She's compiling lists, I think.
Compiling lists.
Yeah.
Fun.
Cool.
Yeah. Oh, also, I think I figured out how to do the download. It should be on the top left down arrow with the thing to download it.
Oh.
I saw that just now, actually, when I tried to do it on this account.
Okay.
Yeah, you can probably cut this out. I don't know.
No way.
I don't care.
It's the new normal.
Yeah, new normal. Well, cool. Yeah, let us know how your students enjoy it.
Yeah, for sure. I think the university is going to request that we make some videos for them to like share with, I don't know, the rest of the world. They seem to be interested in this project, so.
Oh, cool. Cool.
Yeah, hopefully there'll be some attention, Shawn, on this, and we'll be able to get a lot of feedback.
Yeah. Cool. Yeah. Well, enjoy the rest of your quarantine week.
Yeah, you too. We should probably wrap up, but
Yeah.
I'm excited to tell you about the people I've been talking to for future episodes.
Ooh.
Interesting people.
Cool.
We have a sparkling wine expert.
Sparkling wine. Great.
Yeah.
I actually learned in Spain, it's apparently a thing to have sparkling red wine. Can you? I've never imagined sparkling red wine.
Andrea, thoughts?
Yeah, there's like sparkling Pinot Noir. That's really good.
Oh, I've never heard that.
The other day, Andrea put some soda water in one of our older bottles of wine that we weren't really interested in having normally because it was getting old. And that was all right.
The trick that you do when you don't want to taste wine at all.
Well, fair. Yeah, I do like sparkling though. I actually woke up this morning saying, wow, it would be great if I had a mimosa this morning.
Did you
But
have one?
no, because I don't have sparkling. So maybe I'll make a run to the grocery store today
Yeah.
or LCBO, whatever.
Wherever you end up going,
Wherever.
stock up.
I do need to make a grocery run, so yeah. Okay, back
All right.
to quarantine life.
Yeah, back to work.
Yeah.
All right. Well,
All right.
thanks for coming on this ride.
Yeah, no, this was fun. I want to see footage from the students. I want to see their reactions, and I'm really like interested to see the friction on different objects, materials. I don't know like what word to use, and also like the ball bouncing project on the different materials that they choose to use. Yeah, hopefully this data is like open to like people can just look at it.
Yeah, I'll push for that.
Yeah, that'll be cool.
Yeah, if I can just strip the names off of it,
Yeah.
I can maybe like create a couple data sets. We also need a single one or two data sets that if students aren't able to perform the experiments at home, like their computer isn't working or whatever, we need to have some data sets that they can just work with. So I'm sure we'll be collecting data as it comes in and creating several data sets.
Yeah.
That'll be fun.
Yeah. Cool. All right. See ya.
Yeah. See ya.
Okay. Bye.